the previous lecture we were discussing the case of 2 molecules per unit cell and then looking at what happens to the excitons and excitonic bands. For this we solved first the case in which we have 2 molecules and interacting via dipolar interactions, and then we obtained the 2 new states very much like with the hydrogen molecule problem, and the wave functions were just psi plus minus which is here, and then the energy this is the energies. The E plus minus delta is given by E0 plus minus delta. And now what we need to do is see how this phi plus and phi minus are actually propagating through the crystal. In order to do that, let us look at the following. That is, now I have to get the following, that is phi plus H interaction phi plus for the site I to unit cell I to unit cell I plus 1, and then the other one is phi minus unit cell I H interaction phi minus I plus 1, and H interaction is of course the dipolar interaction. So you will get an effective transfer integral for excitation transfer, just as with the sigma 1s and sigma star 1s bands that we had, effective transfer integral. So this will be, let me call it T plus, and here it will be T minus. And depending upon how these excitations are oriented, T minus is usually minus of T plus. So depending upon the orientation of the molecules, in particular the transition dipoles, so T plus can be positive or negative, and if T plus is positive then T minus is negative. T minus will have the opposite sign. So now let us see what happens to the dispersion. Now we will have 2 bands. The dispersions will be like this. So I can say it is pi by 2a and minus pi by 2a, almost like the hydrogenic problem. And you have the ground state here and the excited state. If T plus is negative, then the excited state will have the following, will look like this. So T minus is opposite, so it will go up like that. And if this is for a J aggregate, and if I am looking at the H aggregation, it will look like this. This is again the molecule in the ground state, pi by 2a minus and plus pi by 2a. And what I will have is something going like this. And splitting at k equal to 0, or zone center, is called Davidoff splitting. And even here you will see that the Kasha rule will make sure that supposing I excite an electron from say the ground state to one of these states, let us say. Okay. So what will happen is the excitation will travel down, come here, fall down, and then will travel down here, and then you have a very strong luminescence. So, this is the J aggregate and this one is the H aggregate. In this case, the excitation can be from here to either there or indeed anywhere else, it does not matter. Then what happens, the excitation travels here and falls down and goes down to the lowest energy and tries to emit light from there. So, this is the way it is going, and this is not allowed. So, this is not weakly luminescent, it is. This is strongly luminescent. So, now let me go to a different topic at this now. So, what we have is that our studies of energy levels shows that there are states in the gap region. Okay, so, this is what we showed. So, this is the conduction band, this is the valence band, and then you have got various states around here, even in pure solids, okay, no doping, nothing, but you still have levels in the middle. Now, how does one understand the levels in the middle? In the in gap region. So, in order to understand that, we have to first find out what was missing in our energy band calculations. So, what is the major approximation that was done in energy band calculation? Because anyway, whenever you are dealing with multi-nuclear systems, Born approximation is always made, so it is not an issue. But the major approximation that we have done for the electrons is basically we have ignored explicit electron-electron correlations, explicit electron-electron interactions. So, what we have done is we have just taken a mean potential by averaging the electron correlations over the eigenstates, and then we have replaced the electron-electron repulsions by using this mean potential. This replaces electron-electron correlations. This is a general procedure true for any MO calculation or AO calculation involving atoms, molecules or solids. So, this is a generic approximation. So, given that, for example, when you are looking at say a 2 electron atom like helium atom, let us consider. So, when you are looking at the helium atom, you will see that in this case the AO picture gives you the ground state as 1s2, the 1s orbital having 2 electrons. Now, this is really not true, in the sense that if you ever were to look at find out the orbital in which an electron is found, the true state you will find is that true psi ground state of the helium is actually a very large fraction of 1s2 plus smaller fractions of other configurations like 2s1, 2p1, plus C2 times 2s2 plus C3 times, let me write down one more just for 2s0 or 2s1 3p1, let me make it 2s1. Of course you also have multiple orbitals corresponding to p, d and all that. So this is all the way to all possible configurations you can think of. You have to go to the infinite dimensional space. So given this, what we are finding is that why is it that you are having configurations like 2s1, 2p1? See, when two electrons are in the same orbital, or in 1s, okay, no doubt they are close to the nucleus and so enjoy the electron nuclear attraction. They are close to nucleus, so attractive potential is large. But 1s orbital is also a very contracted orbital in the sense that it is a very compact orbital. So 1s is a compact orbital. So when you put two electrons in 1s, then the electron-electron repulsion is also large. Then perhaps if you have a configuration like 1s1, 2s1, let us say, a configuration like 1s1, 2s1 puts one electron further away from 1s, so it maybe it is having a lesser attraction with the nucleus, but nonetheless there is much lesser repulsion between the 1s and the 2s electron. So the electron-electron repulsion is reduced. So similarly, if you put one electron in 2p x orbital and another electron in 2p y orbital, let us say the configuration is 2p x1, 2p y1, then what happens is one electron is more probable in the x along the x axis, more probable along x direction, another has a larger probability in the y direction, another larger probability along y direction. So because of this, you will see that there is an angular correlation, that is, they are not in the same region in space even if they are on the same spherical surface. Okay. So one of them is more oriented towards the x axis, the other is more oriented towards y axis, so they repel each other much more strong, they repel each other much less. So you see that is the reason why you will have this kind of a mixture of configurations. So this mixture of configurations is called configuration interaction. Is called configuration interaction. Very often they just write it as CI. So when we do a one electron picture, to solve the one electron Hamiltonian, you need linear combination of large number of orbitals, linear combination of large number of atomic or molecular orbitals. Okay, so you require a very large Hilbert space for getting an exact solution. Now supposing we want to have a many electron picture, we need a large number of electron configurations. So, usually you will see that if I plot say number of configurations versus number of orbitals, you will see that this is the place where you will get exact solution. But since our lifetime is finite, we need to get answers to problems within a finite length of time, and so we work in a limited configuration space. So, usually what the physicists do is work in this region, few orbitals but many configurations. This is because you want to get good excitation gaps in the system. You are not so much interested in just the ground state, because most of the times in physics you work with model Hamiltonians, and when you are working with model Hamiltonians, the ground state is energy is arbitrary, the energy of the ground state is shifted by an arbitrary amount, and so what you are really interested in is the gaps between different excitation states. So, for that you will get more accurate gaps the more configurations you take. Whereas in chemistry, the kind of questions you ask often are things like what is the ground state geometry, what is the ground state electron distribution, and many other ground state dipole moment and so forth. So, most of the times you are looking at ground state properties. So, you are looking at here, this is for chemists and this is for mostly physicists. Okay. So, but I mean this is just some arbitrary division. You could be working with very large number in both cases if you have enough computational facilities and abilities. Now, let us see, let us go to a molecular problem now. The simplest molecule that you can think of is the hydrogen molecule. This is the simplest molecule, and what you know is that you are interested in finding out the binding energy of the hydrogen-hydrogen bond, or the bond energy, which is equal to energy of the hydrogen molecule minus twice the energy of the hydrogen atoms. So, this can actually be measured experimentally, and what you have is the following. The experimental curve for EB is actually a function of separation between the two hydrogen atoms. So, what you will get is this energy here and this is R, and so some smooth curve like that you will have, okay, which is actually parabolic at the bottom. So, this goes asymptotically to 0, so that should be the value. But supposing you do a molecular orbital calculation, let us consider MO calculation. So, if one does a molecular orbital calculation, what one gets is somewhat very different. So, one gets something like that. That is, the point to note here is that as R tends to infinity, EB becomes positive. This is EB as a function of R. So, EB as a function of R goes to finite value, finite positive value as R tends to infinity. This is of course wrong, right? And so, what it means is that if you ignore electron-electron repulsions, we cannot even dissociate. We have problem correctly predicting dissociation. of hydrogen molecule. So, it already fails in the simplest case. Now, the important thing is not to just say that it fails and forget, but one has to find out what is the reason. What is the reason for the failure? The reason for the failure is, let us look at the molecular orbital picture. So, here I have the 1s orbital for one hydrogen atom, let me call it H1, and 1s orbital of the second hydrogen atom. They come together, overlap and form a sigma 1s with 2 electrons in that one, and a sigma star 1s with no electrons. This is the ground state in simple MO picture. Of course, this is only schematic, the energies are symmetric around the 0. Now, because of inversion symmetry, in hydrogen molecule around midpoint of the HH bond, it will tell you something, that is, you know that sigma 1s orbital has to be 1 upon root 2 phi 1 1s plus phi 2 1s at all distances, because this symmetry holds at all distances. Similarly, sigma star 1s is 1 upon root 2 phi 1 1s minus of phi 1s of the second hydrogen atom. So, what does it tell you? Now, let us look at the ground state. The ground state is sigma 1s2, that is, there are 2 electrons in the ground state, and because I can write down the ground state as a product of spin state and a spatial or spatial functions, 1s functions. Okay, and it has to obey this thing Fermi exclusion principle. So, if we say, if not Fermi, I mean Pauli exclusion principle is a Fermi statistics. If Pauli exclusion principle has to be obeyed, so if spatial part is symmetric, spin part must be antisymmetric. So, that means that if I have a total wave function of particles 1, 2, etc. up to n, then this will have a spatial part which will go as R1, R2, etc. Rn multiplied by a spin part which is sigma 1, sigma 2, etc. sigma n, where sigma can be either alpha or beta, up or down, whatever you want to call. So, in our case, ground state is a spin singlet, because I have 2 electrons in the same orbital. So, it is nothing but it has to be singlet because of the Pauli exclusion principle, and so I can write down the wave function of the hydrogen molecule in the following fashion: 1 upon root 2 sigma 1s first electron times sigma 1s of second electron plus sigma 1s of second electron times sigma 1s of first electron, and this multiplied by the spin function, which is alpha 1 beta 2 minus of beta 1 alpha 2. So, this will be the total wave function. Now, let us concentrate on the spatial part. Supposing I substitute for sigma 1s, sigma 1s is equal to 1 upon root 2 phi 1s1 plus phi 1s2. Okay. So, if I substitute this one into psi, then the spatially dependent part phi r1 comma r2 will simply have the following. After normalization, I will have 1/2 of phi 1s1 electron 1 phi ns1 electron 2 plus phi 1s2 electron 1 phi 1s2 electron 2 plus twice phi 1s1 electron 1 phi 1s2 electron 2. What does it mean? It means that there is one case wherein the 1s orbital has both the electrons 1 and 2 on atom 1. That is, atom 1 has both the electrons 1 and 2. In this case, this is the 1, and in this case atom 2 has both the electrons 1 and 2, whereas in this case the atom 1 and atom 2 have electrons 1 and 2. That is, if one has electron 1, the other has electron 2, and vice versa. So, I can actually show the whole thing schematically as a resonance diagram. So, the phi ground state of the hydrogen molecule, I can write it as H1 minus H2 plus, which is the first diagram here, because both the electrons are on atom 1 and the atom 2 has no electrons, plus second one is H1 plus H2 minus, and the third one is twice H1 neutral H2 neutral. So, this will be the resonance picture. Now, if I have this resonance picture and then I work out the write down the Hamiltonian for the hydrogen molecule. So, H of hydrogen molecule is just minus h cross squared by 2m del 1 squared minus h cross squared by 2m del 2 squared minus E squared upon R1 minus R minus E squared upon R2 minus R plus E squared upon R12. So, here I have already made the Born-Oppenheimer approximation, but I have not made an approximation for the electron-electron repulsion, which is E squared upon R12. Now, let us see what is going to happen from here on, but we will study that in the next lecture. I will stop at this point for this talk, and I will continue from here in the next lecture. Thank you.